From tracking damaged US assets in the Middle East to showing the devastating flooding caused by hurricanes, there's so much we can see. Today, we are able to see the Earth like never before, but there is also a lot we still can't. We're going to see what modern satellites can show us, what they can't for now, how and why. For centuries, humanity's understanding of the world depended entirely on exploration by land and sea. Every coastline, mountain range, and settlement had to be discovered firsthand before it could appear on a map. The desire to explore the Earth came from many needs, especially travel and navigation, but it was also driven by curiosity about distant places and the people living there. Early attempts to capture views from above were surprisingly creative, using devices attached to kites, balloons, and even birds. Then came World War I, which rapidly transformed aerial observation and mapping technology. As aircraft became faster and more reliable, humans were finally able to rise far above the ground and observe the planet from perspectives never before possible. When World War II rolled around, airplanes advanced again. Pilots flew higher and faster to dodge anti-aircraft fire and spy on enemy lines. But even after the war ended, the drive to go higher didn't stop. Eventually, planes hit a ceiling. They got so high up that the air was too thin to keep their wings working. However, World War II also gave us something else that changed mapping forever: rockets. Scientists in Germany put massive effort into building the V-2 rocket. The new idea became simple. If planes can't fly high enough, let's just strap cameras to rockets and shoot them into orbit. You can't just toss a camera up there though. Even with almost no air, gravity's still pulling things down. The trick to orbiting is speed. If you shoot a satellite sideways fast enough, it falls toward the Earth but moves forward so fast that it constantly misses the Earth. It just keeps falling forever. The weird part is that satellites closer to the Earth actually move faster than satellites farther away. A low Earth orbit satellite can whip around the planet in roughly 90 minutes, while a geostationary satellite takes exactly 24 hours. That relationship comes from Kepler's third law, which links orbital period and orbital size through this formula, where A is the semi-major axis of the orbit. The farther away you go, the larger the orbit becomes, and the longer it takes to complete one lap around the Earth. To stay in this endless freefall, a satellite has to hit an exact speed. This speed is determined using the formula. Here, g is the gravitational constant, m is the Earth's mass, and r is how far you are from the center of the planet. If the satellite slows down below this speed, friction from whatever tiny bit of atmosphere is left will drag it down. But if it goes too fast and hits escape velocity, it will break out of orbit and fly off into deep space. So, technology originally built for dropping bombs turned into the ultimate tool for carrying cameras. Once you're circling the Earth, the view is insane. If we push weather satellites way out into space, they can take a picture of a whole continent in one shot. But that's not always enough. Being far away gives you the big picture. But bringing satellites closer to Earth gives you the fine details. Get close enough and continents turn into cities, and then into individual houses. It's a tough balancing act though. Getting closer to the surface means better pictures, but it also means dragging against the atmosphere, which slows the satellite down while gravity tries to pull it back to the ground. With the launch of the Landsat program in the summer of 1972, instead of zooming in on tiny patches of ground, Landsat was built to monitor massive chunks of the planet all at once. It was like swapping a sniper scope for a wide-angle lens. And the cameras on board kept getting smarter. They started picking up thermal heat and infrared light. The Earth's atmosphere blocks certain types of light, which is good for us, since it stops us from getting sunburns. Meanwhile, plants absorb specific types of light to grow. Because satellites can see these exact types of light, they can tell which crops are absorbing the sunshine and thriving, and which ones are dying. Figuring out plant health relies on something called the Normalized Difference Vegetation Index, or NDVI. Basically, healthy plants absorb normal red light to make food, but their internal leaf structures bounce back near infrared. By running those two types of light through this formula, the satellite can score exactly how healthy the plants are. On top of that, the thermal sensors use Planck's law of blackbody radiation. This lets a satellite figure out the actual temperature of the ground just by measuring specific infrared heat waves. Fast forward to today, and Landsat is still up there taking pictures. It has built an incredible 50-year archive covering almost the whole planet. When you buy a regular camera, you care about megapixels, but satellites don't work exactly like that. Some act like giant telescopes, while others basically scan the ground in one massive endless strip that can end up being 9,000 kilometers long. With a normal camera, detail depends on what you point it at and how close you stand, but satellites are stuck at a specific height in space, and they only have a few lenses, so it just takes some basic geometry to calculate exactly what you can see based on the camera's sensor and the height of the orbit. This is called ground sample distance, or GSD. In simple terms, if you took one single pixel from the camera and painted it on the ground, how big would that square be? You can figure out the ground sample distance with the equation GSD equals P times H divided by F. Here, P is the size of the pixel on the sensor, H is how high the satellite is, and F is the focal length of the lens. But you can't just make the pixels infinitely small because physics eventually gets in the way. It's limited by a rule of optics called the Rayleigh criterion. Theta equals 1.22 times lambda divided by d. If engineers want better resolution, they either have to drop the satellite closer to the Earth or build a much wider mirror, which is the d in that formula. To put that into perspective, Landsat has a GSD of about 30 meters. Sentinel-2 gets it down to 10 meters. That means if you zoom in until the image is blocky, one single pixel equals a 10 by 10 meter square on the ground. But the best commercial satellites we have today can get down to roughly 30 centimeters. At that level, you aren't just looking at blocks. You can clearly see swimming pools, houses, individual cars, or even pick out a specific type of fighter jet parked on a runway. But we're ignoring a massive problem. The thing that old balloon pilots barely worried about is now the ultimate photobomb: clouds. It doesn't matter if your satellite is exactly where it needs to be. If it's a cloudy day, your super expensive camera's just taking pictures of white fluff. You might think we could just use thermal or X-ray cameras to look right through them, but it's not that easy. That's where Synthetic Aperture Radar, or SAR, comes into play. Every now and then engineers invent something incredibly clever and give it a really clunky name. SAR is definitely one of those. Instead of passively waiting to capture sunlight bouncing off the ground, which is how our eyes and normal cameras work, SAR satellites actively shoot down radio waves and listen for an echo. It's basically like a submarine using sonar, but from space. The picture it makes looks like a grainy black and white photo, but it's actually completely different. The coolest part about this tech is that it doesn't care about sunlight or weather. It can see at night, and it can blast right through thick clouds, letting us look at the ground during a hurricane where it would be impossible to fly a plane safely. SAR also relies heavily on the Doppler effect. As the satellite moves forward, the frequency of the returning radar waves shifts slightly depending on where objects are located relative to the spacecraft. By combining echoes collected over time, computers simulate a much larger antenna than the satellite physically carries, which is where the term synthetic aperture comes from. By the way, different radar wavelengths interact with the Earth in completely different ways. Short X-band radar waves mostly reflect off buildings and the tops of trees, while longer L-band waves can partially penetrate vegetation and reveal the terrain underneath. Some lower frequency systems can even punch through dry sand or ice, letting scientists map buried river channels in deserts or hidden lakes beneath Antarctica's glaciers. But the true superpower of radar is tracking changes. With normal photos, you just put an old picture next to a new one and play spot the difference. With radar, you aren't just comparing the pictures, you're comparing the actual phase of the radio waves that bounce back. Because of how the math works, a satellite floating 500 kilometers in space can tell if the dirt on the ground has moved by just a few millimeters since yesterday. This trick is called interferometric synthetic aperture radar, or INSAR. The satellite shoots out microwave pulses and records the exact phase of the wave when it returns. When it flies over that exact same spot a few days later, it checks the phase again. The math for the shift is delta phi equals 4 pi over lambda delta r, where lambda is the wavelength and delta r is how much the ground moved. By looking at how the wave shifted, computers can measure tiny changes in the ground that regular optical cameras could never see. Imagine looking at a photo of a massive city skyline. To a normal camera, everything looks perfectly fine. But radar can track the roof of a single skyscraper and see that it has slowly sunk into the dirt over the last month by just a few millimeters over the last month. It's basically measuring a microscopic tilt in a concrete building from 500 kilometers up in space. It's not magic though. There are limits depending on the radio waves used. If you try to measure a house hidden in a dense pine forest, the radar might just bounce off the top trees and you'd completely lose the signal of the ground below. Still, for the right job, the accuracy is still impressive. If we can track changes down to millimeters and see objects as small as 30 centimeters, isn't this a big intelligence nightmare? Not quite. The big catch is timing. Satellites only give us snapshots, not a live video feed. We only get tiny pieces of the puzzle. Think of it like trying to watch a match, but you only get to see one photograph every 20 minutes. In one picture, the teams are tied. In the next picture, one team is celebrating a massive win. You have absolutely no idea who scored, how they did it, or what happened in between. It doesn't matter if those photos were taken with a $10,000 camera. You still miss the actual game. Plus, you're always gambling with the weather. Half the time, a massive cloud gets in the way and ruins the only shot you get anyway. We also can't just command the satellite to take a picture whenever we feel like it. They're locked into their orbits. If you need a photo of a specific spot, you have to wait for the satellite to pass over it. Most of these imaging satellites travel in polar orbits, meaning they fly roughly over the north and south poles as the Earth spins underneath them. A lot of these paths are set up as sun-synchronous orbits. This means the satellite passes over the same area at the exact same local time of day every single day. To make this happen, the orbit has to shift just a tiny bit, about 0.9856 degrees a day, to perfectly match the Earth's trip around the sun. Engineers do this by using the fact that the Earth is slightly fatter at the equator to pull the satellite into place. The math for getting the right tilt is omega equals -3/2 times J2 times RE over P squared times N times cosine I. By tuning the altitude and the tilt angle, that's the I in the formula, they can lock the satellite's path in sync with the sun. Because the Earth keeps spinning, one satellite might only fly over your target once every couple of weeks. If you want updates faster than that, your only real option is to spend huge money building a whole constellation of them. That's why modern imaging companies launch fleets instead of single spacecraft. If one satellite revisits an area every 14 days, then a constellation of 14 identical satellites spread evenly around the orbit can theoretically reduce that revisit time to roughly once per day. Companies trade launch cost, orbital altitude, and coverage area against how quickly they can return to the same target. Beyond human conflict, this technology is the reason we know so much about climate change. We have decades of unbroken data showing glaciers melting, forests disappearing, but it also shows us how stunning our planet really is.